Bismillahirrahmanirrahim. Here is Dr. Naila Khalid with the course code Chem 322 Organic Chemistry 2. And today is lecture number 8. And the title of your today's study is Elimination Reaction Mechanism Study with special reference to E2 elimination. As you can see in your slide that elimination reaction of this type in which both the reacting species are effective. The rate of reaction is dependent on the concentration of substrate as well as base. So, as it is dependent on two molecular species, that is why it is abbreviated as 2. And one of the group is leaving the surface. One of the group is leaving the surface over here, and you will get elimination product, removal of very small molecule from the substrate with the action of base, in which the rate of reaction is dependent upon 2. The such type of elimination is known as E2 elimination. So in this session, we will discuss in detail what are E2 elimination or what are different factors which affect this E2 elimination. So what I expect from you after this session, you will be able to understand some key features of E2 elimination reaction and its mechanism, and you will be able to elaborate the factors which can affect the E2 elimination reaction. You can be able to explain the competition between elimination and nucleophilic substitution reactions. This is the part of your course, Elimination Reaction Mechanism Study with special reference to E2 mechanism. Up to some extent, these are subtopics which will be covered under this category. So, outline of our present session includes introduction to E2 elimination, mechanism, kinetics, effects of base, stereochemistry of E2 elimination, and substrate reactivity, which substrate is most probably used in E2 elimination and which is reluctant for the E2 elimination, and Z-safe or Z-safe rule. In some books it is written as Z-safe and some it is Z-safe rule. So this rule and the effect of solvent, and then competition between nucleophilic substitution and elimination, and at the end summary of the major points. On this slide number 5, you can see two types of reactions, and you can also see over here the substrate is common. This substrate is secondary substrate. You can say 1, 2, 3. This is 2-bromopropane, or this is 2-bromopropane, secondary bromide, alkyl bromide. And when you treat it with this type of the reagent, this is sodium methasulfide, or you will treat it with sodium methoxide. In both cases, the solvent is common, substrate is common, but the only difference is this reagent. This reagent contains sulfur and this reagent contains oxygen. So you will observe that the substitution product, nucleophilic substitution product in this case, where the sulfide is present, and in case of oxide, sodium methoxide, you will get eliminated product. Why this difference? Actually, sodium methoxide, this methasulfide, not oxide, this methasulfide is a very good nucleophile and weak base. This is a very good nucleophile and it will attack as a nucleophile and remove this bromide. So you will get a nucleophilic substituted product. And the rate of reaction is dependent on the substrate concentration as well as reagent concentration, nucleophilic reagent concentration. So that is why it is bimolecular and nucleophilic substitution. However, if you replace the sodium methosulfide with the sodium methoxide, then its basic strength is very high as compared to its nucleophilic strength. So this base will show elimination product. Why elimination? Because this will not act as a nucleophile. It will abstract this hydrogen from here, electron density comes here, and this bromide is removed. So elimination of this one, elimination of the sodium bromide take place, and you will get this unsaturated molecule as an elimination product. As the rate of reaction is dependent on the two species, substrate and the base. So that is why it is also abbreviated as 2, but as it is elimination, so it is E2 elimination. So that is the difference. So here is also written the rate of reaction in this case, and in first case, the rate of reaction is visible on screen here. Now, this rule is very important to explain at this point. I will say that according to this rule, ZF or ZF rule, according to this rule, the major product, because elimination take place in any way, if there are different types of beta hydrogen, this is our eliminating one of the living group, eliminating species का एक part ये है, and the beta hydrogen here, beta hydrogen here, and beta hydrogen here. It means there are different possibilities. Major two possibilities हैं. If the hydrogen from here is removed, then you will get double bond here. And hydrogen from here is removed, then you will get double bond inside the ring. So according to ZF rule, the most substituted product will be the major product. Both will be the outcome of elimination. But the major product will be that in which the double bond is highly substituted. In other words, ZF rule says that the major product or the double bond which is highly substituted is the most stable product which is formed in this case, and the minor product will be that which is least substituted. So this is the rule, and according to this rule, when alkyl halides have two or more different beta carbons, then more than one alkene product are possible, but only the major product will be that which is the most stable. Which one is the most stable? Which is highly substituted. And this rule, that is why it is called ZF rule. In contrast to ZF rule, on this slide number 7, I will explain Hofmann rule. Hofmann rule is opposite to the ZF rule. It says that least substituted alkene is formed, but it shows some conditions which are present over here. Then instead of the major product, most stable product, only least stable product is formed. जब आपके पास पॉसिबिलिटीज हों दो से दो ज्यादा बीटा कार्बन की, लेकिन जो है उसमें जो है कुछ कंडीशंस ऐसी हों जिसकी वजह से मेजर प्रोडक्ट जो है वो लीस्ट सब्स्टिट्यूटेड प्रोडक्ट बनता है, तो ऐसा रूल हॉफमैन रूल कहलाता है. Now the question arises, what are that conditions, necessary conditions? Why this least substituted product is formed or less stable product is formed, and as contrast to ZF rule? Why? Because of the presence of the bulky leaving group. कोई बेस है, बल्कि लीविंग ग्रुप मौजूद है, जैसे कि क्वार्टरनरी अमोनियम साल्ट है, या बल्कि बेस मौजूद है, उसकी वजह से ये जो है वो मौजूद है, या फिर यह है कि लिविंग ग्रुप बहुत ज्यादा पुअरली लिविंग ग्रुप है। तो पुअर लिविंग ग्रुप है, ये तीन कंडीशंस हैं। इफ द बल्की लिविंग ग्रुप इज प्रेजेंट, क्वार्टरनरी अमोनियम साल्ट की मौजूदगी है, और यानी बल्की बेस है, ये तीन जो है बल्की बेस मौजूद है, या उसमें जो बीटा हाइड्रोजन है वो एग्जैक्ट एंटी पेरिप्लेनर नहीं है। एंटी पेरिप्लेनर का मतलब ये है कि दोनों बीटा हाइड्रोजन और लिविंग ग्रुप एक दूसरे से अपोजिट इन डायरेक्शन है, अपोजिट प्लेन्स में है। ये अगले एग्जांपल्स में हम समझते हैं। और पुअर लिविंग ग्रुप है। तो ये कंडीशंस अगर मौजूद हैं तो देयर इज पॉसिबिलिटी के हॉफमैन प्रोडक्ट जो है वो बने, लीस्ट सब्स्टिट्यूटेड प्रोडक्ट बने, मोस्ट सब्स्टिट्यूटेड प्रोडक्ट ना बने। लीस्ट सब्स्टिट्यूटेड प्रोडक्ट अगरचे लेस स्टेबल होता है, लेकिन इन कंडीशंस की फुलफिलमेंट की बात आप सोच सकते हैं कि हॉफमैन प्रोडक्ट विल बी द मेजर प्रोडक्ट एज कंपेयर टू द सेट्स प्रोडक्ट। Let's see the example. Here on slide number 8, you can see an example where quaternary ammonium is present. This is a very good leaving group. So hydrogen from here, beta hydrogen from here, and beta hydrogen from here can be eliminated. If beta hydrogen from here is eliminated, you will get an elimination product with a double bond here. This is the Hofmann product because it is least substituted. And if the double bond is present, is introduced over here, because this hydrogen is removed, then you will get a most substituted product, and that is called Sedzev product. But in this case, you can see that 95% Hofmann product is obtained, which is least substituted and least stable. The formation is justified by the presence of this quaternary ammonium that is responsible for that is a very good leaving group, and that is bulky base present. So that is why you will get this type of product. Here in this case, this type of substrate, if it is treated first with methyl iodide in excess, you can see that this methyl will act as a methylating agent. It will methylate this nitrogen, and you will get as an intermediate quaternary ammonium salt, and that is responsible for the elimination of the beta hydrogen in such a way that you will get this type of product. Okay, you will get this type of product. In this case, this is the third example. Here the two possibilities are written over here. You can say the fluorine is a highly electronegative, but this is not a good leaving group. This is poor leaving group. So when you treat it with sodium methoxide, which is a base, this will abstract proton from here or here. So there are two possibilities. So this possibility that this hydrogen is removed, and you will end up with double bond outside this ring as a major product. This is called Hofmann product. Why? Because here the fluoride is poorly leaving group, and you will get the Hofmann product as a major product as compared to Sedzev product. As we have also learned in our previous session that mechanism of the elimination reaction is of three different types. E1, which is based on concentration of one molecule, only one substrate, and a bimolecular elimination, the rate of reaction is dependent on two molecular species. And the unimolecular elimination, which involves conjugate base, is another a rare type of elimination, but it is called E1CV. In this session, we are discussing E2 elimination. So here I will give you another example where sodium or potassium ether oxide. So this is ether oxide which is acting as a base, abstracting this hydrogen. This electron density comes here, and this bromide is removing from this surface. So you will get this double bond here. You will get this double bond from here, and you will get this type of product. And here this hydrogen is removed. If it is removed from here, you will get this one propene. If it is removed from here, again you will get one propene. So there is no second possibility because there is only one type of beta hydrogen. But in this case, you can also see only this is the same type of beta hydrogen which are present over here. This one, and this one. So this is alpha position. This is beta. This is beta hydrogen. Only one possibility. If there is one possibility, you will get only one type of product. So that is why one propene. So you will get only one type of product. So as the concentration of both species base and substrate is affecting the rate of reaction, so that is why it is called E2 elimination reaction. This type of reaction is called dehydrobromination or dehydroelimination. Same, you can write, this is the same reaction. You can write the energy profile, draw the energy profile diagram. Here, this substrate and base both are mentioned because the rate of reaction is dependent on both species. And when it gets some activation energy, it can give you a transition state rather than at an intermediate. एक transition state आप यहाँ पे लिखेंगे, and this is mentioned over here, and then it will give you eliminated product. This is an example where only one type of hydrogen, beta hydrogen, is present. What if there are two types of beta hydrogen? Here, this is beta hydrogen and this is beta hydrogen. In case this hydrogen is removed, along with this one, you will get a terminal alkene. And if this hydrogen is removed, along with this one, you will get an internal double bond. This is the major product. And it shows that Sade-Zeff rule is followed over here. Base is eliminating this hydrogen from here and bromide from here, and you will get this as a major product. So this type of dehydrobromination or dehydrohalogenation is called E2 because it follows second order kinetics. Rate of reaction is dependent on two species. So it is also following Sade-Zeff product. This is Sade-Zeff product, and it is regioselective. Why it is regioselective means the position of the beta hydrogen is selectively selected, that which beta hydrogen is more predominantly is more vulnerable for attack. So that is why you will get this type of product. So this is regioselective, position sensitive hai. What are the factors which affect the E2 elimination? A very important factor is the strength of the base. If the base of the strength of the base is very important, if it is very high, strong base will go to E2 elimination, and strong nucleophile will go to SN2. And substrate, effect of substrate is very important, whether it is primary, secondary, tertiary, this is very important. And what type of living group is present, it is also affecting the rate of E2 elimination. And of course, solvent also has its own impact. First of all, the very important factor, that is effect of the base. This is the single most important factor for elimination. If the substrate is suitable for elimination, the strong base will favor E2. The strong base will favor E2. However, weak base can favor E1. But E2 is favored by only strong base. कुछ strong bases आप देख सकते हैं. ये हैं हाइड्रोक्साइड, एल्कोक्साइड, और ये RNH नेगेटिव, और इस तरह मिथाइल के इस पर नेगेटिव. सो कार्बेनाइम है, एमाइड है, ये सारी स्ट्रॉन्ग बेसिस हैं. E2 elimination जो है आप देखें, iodide is a good nucleophile, so you will get nucleophilic substituted product, but ethoxide is a good base as compared to its nucleophilic character. Its basic character is high, so that is why you will get major product as the elimination product. However, 13% nucleophilic substituted product is obtained, but 87 is the eliminated product, that is E2 elimination. These are some of the bases, bulky bases, sterically hindered bases, and strong bases, which go to elimination rather than nucleophilic substitution. Potassium tertiary lithium diisopropylamide, LDA भी उसको कह सकते हैं. ये आप देख सकते हैं पोटेशियम टर्शिब्यूटॉक्साइड स्टेरिकली हिंडर्ड बेस और प्राइमरी एल्काइल ब्रोमाइड को उसने एलिमिनेटेड मेजर प्रोडक्ट एलिमिनेटेड दिया है और ये हमें यहाँ पे डबल बॉन्ड जो है वो अल्कीन डबल बॉन्ड यहाँ पे बना है और ये हॉफमैन प्रोडक्ट है. व्हाई हॉफमैन प्रोडक्ट? बिकॉज बल्की बेस इज यूज्ड. सो E2 को हम देख सकते हैं कि जितने भी फेवर करते हैं वो स्ट्रॉन्ग बेसिस हैं या फिर वो स्टेरिकली हिंडर्ड बेसिस हैं, वो E2 एलिमिनेशन को फेवर करती हैं. तो आपने ये सब याद रखने हैं कि ये दोनों बेसिस जो हैं ये स्टेरिकली हिंडर्ड हैं. E2 एलिमिनेशन को हम बाईमॉलिक्यूलर एलिमिनेशन कहते हैं और स्ट्रॉन्ग बेस इसकी नेसेसरी कंडीशन है. ठीक है, वो ये अल्कोक्साइड, हाइड्रोक्साइड और इस तरह एमाइड जो है वो हो सकती है. इसमें जो लिविंग ग्रुप है और जो दोनों लिविंग ग्रुप हैं, हाइड्रोजन भी और उसके साथ जो दूसरा लिविंग ग्रुप है जो कि डबल बॉन्ड बना रहे हैं, दोनों एक दूसरे के साथ सेम प्लेन में आते हैं, एंटी पेरीप्लेनर होते हैं और ये कंडीशंस फुलफिल होती है तो E2 एलिमिनेशन बहुत आसानी से हो जाती है. E2 एलिमिनेशन के लिए एंटी पेरीप्लेनर का होना बहुत जरूरी है. अगर ये एंटी पेरीप्लेनर ना हो दोनों लिविंग ग्रुप्स तो फिर उसमें जो है प्रोडक्ट जो है वो हमें उस तरह नहीं मिलता है. सो अगर स्टेरिकली हिंडर्ड बेस यूज हुई है तो हॉफमैन प्रोडक्ट बनेगा और अगर जो है स्ट्रॉन्ग बेस है लेकिन स्टेरिकली हिंडर्ड नहीं है तो सेडजैक प्रोडक्ट बनेगा. अब हम ये देख सकते हैं कि बेस ने इसमें किस तरह एलिमिनेशन किया है. यहाँ पे X है और ये किस तरह एलिमिनेटेड प्रोडक्ट जो है वो हमें मिला है. So this is the energy profile diagram for the E2 reaction. If you can say the substrate, the living group has its own impact. The best living group is the iodide and the worst living group is the fluoride. With increase in the size, the living group ability increase. As you know, the living group ability of iodide is very high as compared to fluoride. So if the living group is there, then this is a very good living group, then nucleophilic substitution take place, and if it is this fluoride is the worst living group and least living ability. And a substrate has its own impact. If your alkyl halide is primary, then there most probably it will go to nucleophilic substituted product. Bimolecular nucleophilic substitution take place. However, if your substrate is secondary, there is possibility that all four mechanism may possible and it is hard to predict whether E1, E2, SN1, SN2. So we have to see some other factors. However, in case of tertiary alkyl halides, only SN1 or E1 is possible. So in case of secondary, so we will see some other factors too in order to predict which mechanism is most favorable. Here are some examples with primary alkyl halide. These are all our primary alkyl halide, and in this case sodium cyanide has been used. In the first case, sodium cyanide has been used, and this cyanide is a nucleophile and strong nucleophile. So that is why you will get SN2 product, nucleophilic substituted product. However, if the strong base, instead of sodium cyanide, we have used sodium methoxide, which is a strong base rather than a strong nucleophile, it will give you a nucleophilic substituted product. However, it is strong base. Still, it will not give you an eliminated product. Why? Because the substrate is primary one. This is primary substrate. But with primary substrate and hindered base, this base is not sterically hindered, sodium methoxide. But this tertiary butoxide, potassium tertiary butoxide, is a sterically hindered base. With even primary substrate, it will give you eliminated product, E2 product, rather than this one, nucleophilic substituted product. If your primary alkyl halide is branched one, you will see that if your primary alkyl halide is branched one, like this one, and you have used this type of iodide, you will get SN2 product, nucleophilic substituted product. This is a strong nucleophile, but not so basic. However, if the branched primary alkyl halide is there, even with ethoxide, which is not a sterically hindered base, you will still get the eliminated product. So all these possibilities you have to keep in your mind in order to predict the mechanism, in order to suggest that mechanism. So with poor nucleophilic ability, you will get that you will observe that the reaction will not take place with the primary alkyl halide that is branched one. And with the secondary alkyl halide, you will see that there are also different possibilities. If the secondary alkyl halide is there and it is you are using a polar solvent like ethanol, polar protic solvent, then it is also a weak nucleophile and the bromide is also a good leaving group, then you will get both possibilities. Nucleophilic substitution take place as well as elimination. But in this case, due to presence of this one and good leaving group, you will suggest a mechanism that is SN1 or E1. SN2 SN2 will take place if you have a weakly basic nucleophile. So you will, instead of SN1, it will attack over here and SN2 product is possible only. You will not get any eliminated product. But with a strong basic nucleophile, you will get an eliminated product. And with a tertiary alkyl halide, you will observe that with the polar protic solvent, only SN1 and E1 product are possible. And with a strong base, E2 elimination take place. So all these possibilities are summarized here in the form of a table. You can see each possibility and observe that which type of mechanism is possible. So please keep in your mind all these possibilities and their mechanism when you are suggesting some mechanism for some reactions. So according to the stereochemistry of the E2 elimination, I have also in earlier, I have also mentioned a term anti-periplanar. Anti-periplanar means that both the leaving group, this leaving group and this leaving group, both are anti-periplanar to each other, both are opposite to each other. So this is the Newman projection for this one, and this is the Sahar's projection. Both are the explaining the same anti-periplanar geometry. Ethoxide will attack on the exact opposite in direction to hydrogen. So it will attack on this one, and you will get eliminated product in this way, in this type, in this way. So anti-periplanar is also a condition necessary for E2 elimination. So here, these examples also explain this anti-periplanar geometry. In this case, this is the trans isomer, and you can write this trans isomer in the chair form like this one. Here, this chloride is above the plane, and the hydrogen is also above the plane. So below the plane, it is also axial and it is equatorial. So you can say this is di-equatorial form. You can also write it in this way, a diaxial. And here the chloride and hydrogen both are anti-periplanar. ये पहले अपने आप को कन्फॉर्मेशनली अरेंज करता है और उसके बाद ये एलिमिनेशन होती है, जबकि सिस आइसोमर में चूंकि ऑलरेडी वो एक दूसरे के एक्सियल पोजीशन पे हैं तो ये फास्ट होता है रिएक्शन. ये आप देख सकते हैं, you will get this major product. Similarly, this is isomer in which this bromide is above the plane, means it is axial. Then this hydrogen, which is anti-periplanar to this one, it is removed. and you will get this type of product. And in case of trans isomer, it has to arrange in the form of anti-periplanar position, and then this is converted into elimination product. So anti-orientation, anti-periplanar, both are same. So these are the conditions necessary for elimination. So this is also here you can say this hydrogen and this bromide. These are anti-periplanar, you will get this type of product. These hydrogen and this hydrobromide and this one, in this case, both are, this bromide is above the plane, this is below the plane, this is above the plane, this is the below the plane. So in this case, you will get this type of product. Dehydrobromination take place in both cases, and the base they have used is potassium buta oxide. So here I have summarized some factors that the effect of the base of strength, if it is weak base, then halides, this one, this nucleophilic substitution take place with the weak, this one, this strong bases, elimination take place with the weak one bases are strong nucleophilic substitution take place. Here the elimination take place with a strong basis, with sterically unhindered bases, substitution predominate, and sterically hindered bases, elimination predominate. Sterical hindrance of the strong basic nucleophile. If sterically unhindered nucleophile are there, then substitution is the most major product. And if the sterically hindered nucleophile are there, then elimination is favorable. Again, this is summarized in the form of a table in order to give you idea that where the SN2 take place, stereochemistry is inversion. SN1 take place, racemic. E2, anti-coplanar, Sedgwick rule is followed. And E1, Sedgwick rule is also followed, but the rate of reaction in each case is written over here. Rearrangement is possible only in case of SN1 and E1. So summary of the E2 reaction, second order kinetics को follow करता है. Mechanism is single step, concerted one. So you have to identify that which R group is there. Is it most substituted? Primary alkyl halide है, secondary है, tertiary है. तो rate of reaction जो है वो सबसे ज्यादा जो है वो किस पे डिपेंड करता है. इसी तरह स्ट्रेंथ ऑफ बेस के बारे में हमने डिस्कस किया. लिविंग ग्रुप की एबिलिटी जो है वो बेटर लिविंग ग्रुप विल लीड टू द E2 एलिमिनेशन, and polar aprotic solvents will favor the E2 elimination. So E2 elimination reaction stereo selective भी होते हैं. Trans double bond जो है वो preferably जो है वो बनता है. So this is the summary and end of our session.